Okay, welcome. System Devices 1, Lecture 5b, the computer, where we start to think about how we implement the simple CPU's block diagram in hardware. So in the last lecture we looked at how the computer would implement the fetch, decode, execute cycle. So you should have a good idea how the processor processes an instruction. But now we need to look at how we will implement this in actual hardware. So how do we take those AND gates, OR gates, those counters, those adders, those multiplexers we saw in previous lectures, and build this processor. So this is the instruction set that the simple CPU supports. So we've got our basic 11 instructions. And we saw in the last lecture and the CPU Sim Labs, how these will be broken down into a series of steps, a series of microinstructions inside the processor. Well, a microinstruction is just the state of the control signals within the processor for each phase of the machine level instructions execution. And each element within the processor will have one or more control signals. So the instruction register, for example, will have one control signal telling it when it should update its contents. And obviously that will be updated during the fetch phase. The ALU, on the other hand, will have multiple control signals because we'll have to configure it to perform different operations. So these will be the add, the subtract, the bitwise AND, and the pass-through operations. So each of the processor's components will have one more control signals. When you add those all up, this is what this table here is showing you. So you can see the control signals associated with each component. So the program counter has got two signals, enable and a load. The instruction register, as you mentioned, just got one, it's enabled. The accumulator's got one. The ALU has three, the two multiplexers have one each, and the memory has three control signals. And this table here shows you the state of all those control signals for each phase of an instruction's execution. So each row is a microinstruction within the processor. So you can see here's our machine level instructions, our move, our add, and our subtract, etc. going down. So each row shows you the state of the control signal for that phase of that instruction's execution. When you first look at this truth table, it can be a bit confusing, so we'll just have a quick look at some of the features in detail. As discussed previously, these signals here are outputs from the control logic, enabling or disabling certain functionality for each of the processor's components. These signals here are inputs to the control logic, indicating what phase the instruction is currently in. We'll see later in the lecture this is generated by a ring counter. So if we took the move instruction, for example, we can see the state of the control signals at the fetch, decode and execute phases. And the state of the processor is represented as a one-hot value. So in the fetch phase, what we need to do is enable the instruction register. And you can see here the instruction enable register's control signal is only active during the fetch phase. It's disabled in the decode and execute phases because we don't want it to update. Again, intuitively you can see that the accumulator enable signal is only enabled during the execution phase, at the end of the instruction, when you're updating the result. So for each of these control signals, have a look back in the block diagram and see if you can see when they should be active and when they are inactive. A good one to start with is the address select signal. So this goes to the address multiplexer. So if you go back and look at the block diagram, it's this multiplexer here. So you're either selecting input 0 or input 1. So when this control signal is a 0, you'll select the program counter. And when it's a 1, you'll select the operand field from the instruction. When it's a add memory, subtract memory, or load or store. So when we come back to the truth table, you can see that there's only a 1 when it's the load, a store, an add memory, or subtract memory. In all other cases it's a 0 because we want to use the program counter. We don't want to use that operand field. Okay, now we can convert this truth table into a series of Boolean equations. So each row here is an output from the control logic, a column in the previous truth table. And these equations here generate the required logical 1 outputs for each control signal, given the current processor's state, so whether it's doing a fetch, a decode, or an execute, and dependent what machine instruction it is currently executing, whether it be a load, a store, an add, etc. The syntax here is from the bedboard implementation of the simple CPU, and these equations were used to program the PLDs, the programmable logic devices. They are written in an enable HDL syntax, so enable advanced Boolean expression language syntax, where a logical AND is an ampersand, a logical OR is a hash, and a NOT is an exclamation mark. Again, go back to the truth table to see if you can see how these equations were generated. A nice easy one to start with is the instruction register enable. Obviously that is only true when you have a fetch, and you can see here instruction enable, and is only a 1 when the fetch input is a 1. It's a 0 in all other situations. So this is common to all machine level instructions. However, to understand some of these other control signals, you need to know the underlying hardware architecture. So for example, the ALU control signals. So this is our ALU. You can see that the control signal 0 is used to select whether the adder subtractor unit does an add or subtract. So when it's a 0, it does an add. When it's a 1, it does a subtract. The other two control signals select which functional unit is routed through to the output of the ALU using this 3-input multiplexer. So you can see when these control signals are 0, 0, we select the adder subtractor output, and when it's 1 we select the bitwise and when it's 2 we select the pass-through function, so B just passes through to the output. These Boolean equations can then be converted into the schematic representation, so these logic gates here are the realization of these equations that define this truth table. The inputs to this control logic are generated by this decoder and the ring counter. The ring counter is used to define the processor's state. So what we have with this component, as we saw in previous slides, we've got our clock and clear inputs, and we have 3 outputs, Q0, Q1 and Q2, defining whether I'm in a fetch, decode or execute phases. So on each clock cycle, the counter will be incremented. So on reset, the Q0 signal goes to 1, indicating me in the fetch phase. On the next clock cycle, the 1 passes through to the next output, so I'm doing a decode, then execute, then it overflows back to 0 to indicate I'm fetching the next instruction, and it just repeats through that cycle. To indicate which machine level instruction the processor is currently executing, we decode the top 4 bits of the instruction register, that opcode field. So those top 4 bits go into this decoder. This is a binary to 1 hot decoder, so 4 bits in, 16 possible outputs. So the simple CPU is only using the first 11 outputs, so Y0 to YA. For its machine level instructions. We could use these spare bits for other instructions, so we could add more functionality to the processor by defining new instructions. So if we looked inside this component, we'll just see it's our standard decoder. So we take the non-complemented and complemented versions and pass them to 4 input AND gates, and each AND gate has a different combination of those signals, so that only one output will be set to 1 at any one time. So if we zoom in, just look at this one in detail, so we can see when we have an opcode of all zeros, obviously that's inverted to all 1s. So this AND gate here is the only one which will be producing a logical 1 to indicate we're doing a move instruction. If the next instruction contains opcode 1, then obviously one of those bits will go to a 0, disabling that AND gate, but this one here now goes to 1, indicating we're doing an add instruction, because obviously opcode 1 is the immediate add instruction. So if you go back and look at the instruction set for the processor, you'll see each one of these AND gates here will go to a logical 1 when its opcode is in the instruction register. So now we have all the hardware components needed to implement the control logic or the control element of our processor. So with the decoder, ring counter and the logic we generated from the previous truth table, we can now generate the required MicroInstructions to perform each machine level instruction. Again, just to show that in a little bit more detail, you can see here the realization of some of these equations in the actual logical circuit. So if we take the instruction register enable signal, you can see that's just driven by fetch, and that's what we've got here. So from our ring counter, the Q0 output, which indicates that we're doing a fetch, is just routed through a buffer to that instruction register enable signal. The RAM write enable control signal is only generated during a store instruction, because the store instruction is the only instruction that can write to memory. So you can see when I'm doing a store and I'm in the execute phase, the RAM write enable signal will be set high. So we have the Q2 output of our ring counter indicating I'm doing an execute phase, and the Y5 output from the decoder indicating that I'm executing opcode 5, the store instruction, adding those together to generate our write enable signal. Okay, a quick quiz to see if that made sense. Can you draw me the schematic control signals for the ALUs? So these 3 Boolean equations. You may want to pause the video as the answer follows. So this is the schematic of the simple CPUs. So we've got the accumulator, the ALU, data mux, control logic, program counter, instruction register and address multiplexer. So if we look inside the control logic, you can see these are the control signals that we're generating, and the ones we're interesting at the bottom here. So if we zoom in, so control signal 2 uses a single OR gate, which all together the move signal and the load signal, and obviously they come from our 1 hot decoder, so the move signal and the load signal. Control signal 1, that's nice and easy, so that's just the bitwise and control signal 0 uses an OR gate, ORing together the sub M and the sub control signals, again from the 1 hot decoder. Okay, no rest, another quick quiz. What modifications would you need to make to the processor to add a new multiply instruction? So an instruction can multiply together the value stored in the accumulator and a constant in one instruction. To help you start thinking about that problem, here we have the schematic of the ALU, and here we have the 1 hot decoder we saw in the previous question. A final question, what problems could occur when we're storing the result of a multiplication, compared to if we're storing the result of an add or subtract, for example? You may want to pause the video here and work through this one as the answers follow. So our new multiply instruction uses the immediate addressing mode, so you can see we're multiplying the contents of the accumulator by a constant and storing the result into the accumulator. Therefore, most of the control signal will be exactly the same as the move instruction. We need to add an additional functional unit to the ALU. So we need to add a 4-input multiplexer, and the spare 4th input will now be attached to our multiplication hardware. And as we saw in the lab, we can build that using an array of adders. That will multiply the values A and B coming in. So take those values, multiply them together, and we can pass that through the multiplexer to the output. Obviously, we will need to assign this new instruction a opcode, and I can choose any of them from opcode 11 to 15 because they're unused in the one-hot decoder. One possible problem that could occur with the multiplication is that if you multiply two 8-bit numbers together, you could generate a 16-bit result, and obviously our accumulator is only 8 bits, so the result wouldn't fit into our general purpose data register, so that would be an issue. Okay, now we're going to move on and look at the process memory, because there's a couple of things we need to consider about how we represent data and how we represent instructions. So the size of your data is dependent on how big a number you need to represent and what format you'll be using. So is it signed, unsigned, and the range of values it'll need to represent. So this processor, we're going to stick with an 8-bit value, so we can represent plus 127 to minus 128 as a signed value, or 0 to 255 as an unsigned value. And that will allow us to do the calculations that we need to do for these particular examples. However, the instructions require 16 bits. So again, if you look back at the bit fields used in the instruction, we need a certain number of bits to represent the opcodes and the operands that we need to process. So these two widths are independent. There are some couplings between the two, but the size of the instruction and the size of the data are generally independent of each other. So this raises some questions about how we configure our external memory. What happens when you read or write data to a memory location, because each memory location at the moment is 16 bits in size, because obviously we'll be reading and writing an 8-bit value from a 16-bit storage location. So when I was designing this processor, there were some choices to be made. I could have made everything 16 bits, so I could have made the data 16 bits and I could make the instruction bit 16 bits. So everything was the same size, so that kind of removes the problem. The downside to that is obviously you increase the size of the ALU. You have to increase the size of the adder, the bitwise and the data paths within the processor, which all takes space. And if you're not using 16-bit values, then that's just wasted hardware. An alternative solution would only be to read and write to 1 byte of each memory location. The advantage of that is it simplifies the hardware. Downside is you're wasting half your memory for each storage location. So each memory location stores 16 bits, so if you only ever read and write to the lower 8 bits, you're wasting half of that memory. Alternatively, you could make the memory 8 bits wide, so each memory location stores 8 bits rather than 16. That's fine now for when we're doing read and write, so we can read and write to each memory location. Downside is obviously the instructions are 16 bits, so an instruction now would have to be spread across 2 memory locations. So when you did a fetch, you'd actually have to read 2 memory locations. So you'd read the low byte and the high byte in 2 separate transactions, storing those into the instruction register to make your 16-bit instruction. Alternatively, we could go to byte addressable memory. So here, rather than having one memory that stores 16-bit values, we pick that memory, split it into 2 memories, each storing 8-bit values. Okay, when you first look at this block diagram, it may be slightly confusing, so we'll take a step back and consider the original CPU architecture. In that original machine, we actually had 512 bytes of memory, because we had 256 times 16-bit memory locations. Therefore, when we go to byte adjustable memory, we actually have to halve the amount of memory we have, because we are still constrained by the 8-bit address bus. So now we'll have 256 times 8 bits. If we wanted to keep the same amount of memory, to have 512 bytes of memory, obviously we'd need to go to a 9-bit address bus. Okay, the first thing to point out is that each memory stores 128 bytes, giving us our 256 8-bit storage locations. As each memory only stores 128 bytes, we only need a 7-bit address bus. So address lines 7 to 1 are used to address each memory. So these 7 wires are connected to the 7-bit address bus of the memory. From the memory's point of view, their address lines address 6 down to 0. The processor's data out bus, again, is connected to the accumulator, so that is just an 8-bit value. And you can see that goes to both memories. So the same 8-bit value goes to both of these memory devices. However, when we do a write operation, only one of these memory devices will be enabled. So during a store operation, the address goes out, addressing the memory location that we want to access. But you can see here the write enable signal, the control signal tells the memory that the write operation is controlled by address line 0, the unused address bit from the address bus. So when the processor performs a write operation to an even address, the least significant bit of the address bus will be a 0. You can see it will write only to this memory. That 0 will disable this memory.
When it writes to an odd number address, you can see it will be writing to this memory, address 0, so enabling this AND gate and disabling this AND gate. Therefore, we consider this memory to be the low byte and this one to be the high byte. So separating our memory into two blocks and only enabling one at a time overcomes one of the problems we were trying to solve, the ability to write to every byte in memory. But we still need the ability to read each byte when we execute a load instruction. And that's what this output multiplexer here allows us to do. So when I perform a read operation, again, the address comes out onto this address bus, identify the location I want to read. Both memories will be accessed, but only one of them will be driving the data onto the low 8 bits of the data bus going into the processor. And again, that selection is made by address line, address 0. So when that address line is a 0, you'll select the 8 bits from the low memory, and when it's a 1, you'll select the 8 bits from the high memory. And that 8-bit value is routed through the processor and stored into the accumulator. Finally, we need to be able to access a 16-bit instruction in one memory transaction. And again, that is possible with this architecture. So again, when you're performing an instruction fetch, the address of the instruction you want to read is placed onto the address bus, and then the high byte drives the high 8 bits and the low byte drives the low 8 bits. But a key thing to identify here is that an instruction needs to be aligned on a word boundary. So we'll look at that in a little bit more detail on the next slide.
Okay, quick quiz. So how will moving from a 16-bit memory to an 8-bit memory affect our multiplication program? How will it be stored in memory? So here we have our multiplication program. This is its machine code. This is binary representation. And normally each instruction is stored in one memory location as a 16-bit word. But how will that transition to byte addressable affect this? As always, you may want to pause the video now and work through this as the answer follows.
So you can see here, this is our multiply 10 by 3 program we saw in a previous lecture, and this is taken from the original architecture where these instructions were stored in one memory location. So you can see here, here's the assembly language, here's that represented in machine code in hexadecimal format, and here is the same instruction represented in binary. So originally each instruction was stored in one memory location, so this will be stored in address 0, address 1, address 2, address 3, etc. going through. But now when we move to byte addressable memory, each byte has to be stored in a separate memory location. So you'll take this 16-bit machine code instruction and split it across two memory locations, and that's what I'll try to show in this table here. So each address here, so address 0, address 1, address 2, now stores only 8 bits. So you can see that the move instruction is spread across two memory locations, so address 0 and address 1. The store instruction, again, is spread across two memory locations, so the 50, the 0D, 500D is spread across address 2 and 3. We can now view that by placing these memory locations side by side so that we can see the full 16 bits in one row. This will be the low byte and this will be the high byte. So low byte, low byte, high byte, high byte. However, if you look at the store instruction, you can see this has changed. Again, low byte, high byte. So the high byte, obviously containing the opcode, remains the same. But the low byte, the address, has changed. And that's because we've gone from a 16-bit memory to an 8-bit memory. In the original program, if you go back here, we're storing the data value out to address D, address 13, because that's the next free location. But as each instruction now takes two memory locations, the address that I want to write to is effectively doubled. So rather than 13, it goes to 26. And obviously, if you know your hexadecimal, I've got 116 and a 10, so 26 there. And the key advantage of this is obviously we save memory. So in the original program, I needed two memory locations to store my two 8-bit values. And that was actually taking up two 16-bit memory locations, or 32 bits worth of storage. And I was only using half of that to store two 8-bit values, or 16 bits. In the new byte addressable memory, obviously I used two 8-bit storage locations because now I can address every byte in memory. So I store one variable to address 1A and the other variable to 1B. So going back to considering how instructions are stored in memory, we can see that they have to be aligned to even address boundaries. So you can see instructions start at address 0, 2, 4, 6, 8 going through. So now when we increment our program counter, rather than increment it by 1, like we did in the previous architecture where each memory location stores 16 bits, we have to increment it by 2 to get to the next 16-bit value. Finally, another thing to consider when you're looking at byte addressable memory is actually how do you store those 16-bit values in memory? Do you store the high byte or the low byte first? In this case here, we're storing the low byte into the first addressable location, and we call that a little ending representation. But equally, you could have stored, in this case here, the 50 in that first addressable location. Obviously, that makes no difference to the processor. It knows the order the data will be stored, so it can read it back in the correct sequence. But it's a design decision to be made. If you store the low byte in the first addressable location, we call that a little ending representation. If you store the high byte in the first addressable location, we call that big ending representation. For this processor, when it's reading or writing variables from memory, it can only read and write to the low byte of each 16-bit storage location. You could argue, why have I got a 16-bit data bus then? Because instructions are only 12 bits, as instructions don't actually use the low nibble of the high byte. And the reason for that one is we do use those extra bit fields in later processors, so that's why I went for a 16-bit address bus. So here we have the data out bus of the processor, so the 16-bit bus. The lower 8 bits comes from the accumulator. The higher 8 bits aren't actually used by the processor, but we can do some interesting things with self-modifying code here. So the key thing to remember here is that an instruction is just a bit pattern stored in memory, and as we can write to memory, we can change that bit pattern. Then if we tell the processor to execute the storage location that we have modified, it will actually execute that bit pattern as an instruction. So therefore we can change the instructions at runtime. However, to allow us to do this, we have to have the ability to change all 16 bits. And as we saw previously, we can only change at the moment the lower 8 bits when we do a store instruction. So this is our store instruction. So we have a 4-bit opcode field, 4 bits are unused, and an 8-bit operand field, which contains the address that I want to write to. Therefore, what I've done was, rather than just encoding zeros in this unused bit field, I've actually used it to store a new opcode value. So the new and improved store instruction is given here. Again, I have the same opcode value for the store instruction, but now this bit field stores the opcode of the new instruction that I want to create in memory. And again, this stores the address that I'll be writing to. So now when you execute this store instruction, I'll actually write these values into the specified memory location. So at address B, I will write whatever's stored in the accumulator to the lower 8 bits as normal. However, the high nibble in the high byte is updated with this new opcode value stored in the store instruction. So this value here will be written to the high nibble. And as always, this bit field here, the low nibble of the high byte, is just written to the constant 0. And that's what you can see in this schematic here. So here we have the low byte is updated with the accumulator value. The low nibble of the high byte is set to a constant 0, so that's a constant symbol. And the high nibble of the high byte is set to that 4-bit bit field coming from the instruction. So what that allows me to do is to write at runtime a new bit pattern into memory that represents the instruction that I want the processor to execute, self-modifying code. So in this example I've written the value stored in the accumulator, which happened to be the value 44, into the low byte to the value 8 in this example. And opcode 8 is a jump instruction. So effectively what I've done is written the bit pattern into memory for jump 44. So when the processor executes this new instruction at address B, it will actually perform jump 44. Obviously, a program that rewrites itself at runtime is a very bad idea, makes debugging very difficult. But these ideas were used extensively in first and second generation computers to simplify their hardware. An example of that is a Wheeler jump. So this is the first example of a subroutine call used in a processor. It was actually used in EDSAC, that first generation computer we looked at in the first set of lecture slides. So here we have the pseudocode of the software function I want to implement. So I've got a variable, initialize it to a value, then I call a function on that variable to update a new variable. The function declaration is down here. So this function takes the parameters that I pass to it, multiplies by 2, and updates the x obviously now with 44. And that can be implemented with this code here. So this function will be stored at a fixed location in memory, and it can be called from any part of the user's program. So we need a way of working out which address we need to jump back to in the user's program. So if you actually look at this code here, this is what it's actually doing. So here we have our assembly language program. Remember, code, function, exit, and data, symbolic labels. They were just addresses in memory. So when we execute the instruction move code, normally when we execute a move instruction, we're moving data into the accumulator that we want to process. But here we're actually moving the address of the instruction into the accumulator. So move code moves the value 10, because that's the address that is stored in this example, into the accumulator. And then we jump to our function, which is at address 50, and that's fixed, obviously. So by moving the address of the move instruction into the accumulator, we're giving ourselves a reference to where we want to jump back to. So when we finish the function, we want to jump back to address 12. That's the next instruction in the program. So every time we call the subroutine, every time we perform a Wheeler jump, we first have to load the address we're coming from into the accumulator. Then we add 2 to it to generate the return address. So in this example, it had the value 10, add 2, become 12. So 12 will be the instruction after the jump instruction. Then we have to use self-modifying code to modify the jump instruction at the end of the function, overwriting the address that was specified with the address that I want to jump to. And that's what this new store instruction does do. Again, the store instruction just writes to the address specified by this symbolic label, so exit, so that will be address 54 in this example. So it will write to address 54 the value 12, but it will also set the high nibble of the high byte to the value 8, which is the opcode for the jump instruction. So effectively we've rewritten this instruction. So in this example, the opcode value remains the same. It's the value 8, a jump instruction, but I have changed the jump address to address 12, returning me back to the main program after this function call. So once the function has generated its return address, it then performs its functionality. So I load into the accumulator the data specified by the symbolic label data, so address 55 in this example here. So I load the value 22 into the accumulator. Then I add to that the data stored at address 55. So again, just 22 plus 22, so multiplication through repeated addition. Finish my function by jumping back to the main program, returning the result in the accumulator to be processed by later instructions. So that is an example of a Wheeler jump using self-modifying code to perform function calls. In later versions of the simple CPU, we removed the need for self-modifying code, because obviously that's a bad idea, and introduced two new instructions, the call and return. But these do come with a hardware cost. We need extra architectural units to implement these instructions. So a quick summary. We had a look at how we actually generate the control logic within the processor. So we looked at how we can convert the machine level instructions down into a series of microinstructions, that step-by-step series of control signals that implement each instruction. We considered how the memory will be organized. So do we use 16-bit addressable locations or byte addressable memory? So if we use byte addressable memory, do we use little or big endian representations? And then we saw how we could use self-modifying code to increase the functionality of our processor. Again, just to be clear, not a recommended programming technique. Okay, I think that's where I'll leave it there, and we'll continue in lecture 5C.